Welcome to our third video lecture. In this session, we will go over the materials that will be covered in exam 1, and then we will use the rest of the time to briefly comment on the problems in the practice exam. All right, so here I list what I call knowledge points. I'm going to quickly go over them, briefly explain what my expectations are. I'm trying to be as specific as possible. So there are basically four chapters that we covered in the past month. The first part we covered is basic quantum mechanics, atomic electronic structure. In this section, my expectation is that you understand and remember the basic concepts and properties of atomic orbitals. Okay, so this include the symbols, for all the quantum numbers and their meaning, the shape of the atomic orbitals, their symmetry properties with respect to the XYZ axis, or with respect to other symmetry elements. For some atomic orbitals, there are positive and negative signs, and you should be able to correctly sketch the shape of those atomic orbitals and assign them the correct signs. In addition to that, you should understand very well the rules associated with electron filling into atomic orbitals. You should be able to predict and sketch the ground state electronic structure of all first and second row elements, and be able to explain certain electronic configurations of transition metals that do not follow the rules. Okay, for example, certain transition metals prefer half-filled or fully filled subshells. Okay? And also in this section, we also talked about periodic trends. We talked about size. We talked about ionization energy, electron affinity. And in those discussions, we talk about the general trend, for example, from left to right and from top to down. But equally important is the elements that do not follow the trend, the general trend. For example, in the discussion of ionization energy, we discussed why nitrogen and phosphorus showed much higher ionization energy than both its left side neighbor and right side neighbor. And that's a result of the half-filled subshell of 2p and 3p in those elements. So you should be able to understand those anomalies in addition to the general trend of those atomic properties. In the second part, we discussed symmetry. Here, my expectation is that you understand all the symmetry elements and their associated symmetry operations. You should definitely remember the signs associated with those elements and operations. Now, keep in mind, certain symmetry elements can generate multiple symmetry operations. For example, a proper rotation axis can generate Cn to the second order, third order, fourth order, all the way to Cn to the nth order. And some of those operations have equivalent symmetry operations. For example, Cn to the nth order is essentially identity operation. Okay? So you should be able to understand and be able to derive those equivalent symmetry operations as well. In addition to that, within the context of molecular chemistry, you should be able to identify symmetry elements within a molecule, because this is the requirement for you before you can assign a symmetry point group to a molecule. So you should first be able to identify symmetry elements, and once you can do that easily, you should be able to follow the flow chart to assign a point group to the molecule. Okay? And the flow chart, as I said, will be provided in the exam. The level of difficulty I would expect in the exam is similar to the practice exam that you have worked on. Um, all right, in the third part, we discussed VSEPR theory. Here, the expectations are you can calculate the steric numbers by correctly counting the number of valence shell electrons and identify the number of ligand atoms and the nature of the bond between the central atom and the ligand atoms, whether it's a single bond or double bond, so on and so forth. And once you can do that, you can calculate the number of lone pairs on the central atom, and you add up the lone pair and the ligand atoms, you can come up with the steric number. You should remember very well all the geometries associated with steric numbers 2 to 7. Okay. So those are linear, trigonal, tetrahedral, and steric number 5, that's trigonal bipyramidal. And number 4, steric number 6 is octahedral, and 7 is pentagonal bipyramidal. On top of that, you should be able to predict molecular shapes. Basically, the tricky thing here is where to put lone pairs and multiple bonds. How do you minimize the electron pair repulsion by placing lone pairs and multiple bonds at the best location? Typically, the most tricky molecule would be associated with trigonal bipyramidal configuration. Okay, so you should be able to name the typical shapes of the molecule. For example, linear, triangular, square planar, seesaw, T-shape, things like this. If you can name them, if you cannot name them, you should at least be able to sketch the 3D shape of those molecules. Okay? You can either include or not include the lone pair in describing the shape, but I would recommend you include the lone pair because that makes it easier for me to understand the 3D structure of everything. All right, and the side discussion in this part is resonance structure. We briefly discussed what those structures are, and the important thing to remember here is that resonance structures are not equilibrium. Okay? The resonance structures as a whole describe the nature of the molecule, okay? And the molecule does not exist at one point in one resonance structure and at another point in another resonance structure, but rather the collective properties of those resonance structures describes the overall property of the molecule. All right, and once you draw the resonance structures, you should be able to make assessment about their relative stability. And there are discussions we had in class about which resonance structure is most stable. Basically, more bond is more stable, less charge separation is more stable, and if there has to be charge separation, you would rather have the negative charge on the more electronegative elements. So once you make assessment on the stability of those resonance structures, you can identify the resonance structures that make important contributions to the molecular property, and based on that make predictions. For example, how long the bond would be. Is it going to be more like a single bond or more like a double bond or somewhere in between? Where the charge is going to be, and what's the dipole moment and things like this. Okay. In the molecular orbital theory, my expectation is that you should be able to construct simple MO diagrams, and simple means for diatomic molecules, and the diatomic molecules could either be homonuclear or heteronuclear. You should be able to correctly connect the MO energy levels with the corresponding atomic orbital energy levels. You should be able to identify the nature of the bond, whether it's a sigma, whether it's a pi, whether it's a bonding orbital, non-bonding, or anti-bonding orbital. And on top of that, you should be able to fill electrons into the molecular orbitals and be able to calculate bond order, and from which to predict molecular properties. We also had a discussion about multinuclear molecules. In those cases, I do not expect you to produce a molecular orbital structure. Instead, if I give you a molecular orbital structure, I expect you to use the MO diagram to correctly interpret it and to predict molecular properties. Okay. All right. In the next couple of slides, I want to quickly go over the selected problems in the practice exam. Some of the problems are pretty simple, so I'm just gonna focus on the probably more puzzling ones. All right, the first question is about electronic configuration and the periodic table. The first question is pretty easy. It's about basically the trend of ionization energy, and it's self-explanatory. The second question is also pretty easy. It's about how the nuclear charge impact atomic radii. All those three species have the same electronic configuration, but they have different number of nuclear charge. Okay, so in this case, higher nuclear charge would produce a smaller atomic size. Okay, I'm gonna skip 1D and 1E. So 1E, it was required last semester, but we did not discuss this in the lecture. So you're not required to calculate the effective nuclear charge, but rather you should understand the concept. All right, VSEPR theory. Here I have the answer key copied, and on the right hand side I listed the steric numbers I calculated for each of the molecule. Okay, so for dichloromethane, carbon has 4 valence shell electrons. Each hydrogen and chlorine would require 1 electron. So a total of 4 ligand atoms require 4 electrons to form covalent bonds. And there's no lone pair, so steric number equals 4. And the ideal structure is tetrahedral, but in this case, there are 2 kinds of ligand atoms. So this will be a distorted tetrahedron instead. The second structure, sulfur tetrafluoride. Sulfur has a valence shell electron count of 6. Now it uses 4 to form 4 single bond with each sulfur, and that leaves 1 electron lone pair. So the steric number will be 1 lone pair plus 4 fluorine atoms, so a total of 5. So the ideal structure is trigonal bipyramidal. Now in this case, there's a lone pair. We have discussed this situation in class a number of times. To minimize 90-degree interaction, the lone pair should be placed on the equatorial position. Okay, so in this case, you will only have 2 90-degree interactions. The presence of the lone pair will also push the 2 axial location fluorine atoms a bit further away from the lone pair. So the overall shape would be a seesaw. This third one, selenium trifluoride cation. Selenium has a valence shell electron count of 6. It uses 3 to form 3 bonds, and there's a positive charge. So you do 6 minus 3 minus 1, and you take the results divided by 2. You end up with 1 lone pair. So 1 lone pair, 3 fluorine atoms. So this is equivalent to ammonia, basically. So that's a pyramidal structure, just like ammonia. Iodine, oxygen, and 5 OH. Okay. Steric number should be 6 because iodine has valence shell count of 7. It uses 2 electrons to form a double bond with oxygen. and five electrons to form 5 single bonds with each of the hydroxyl group. So a total of 7 electrons involved in covalent bonding. That leaves no lone pair. So in this case, each OH is counted as one ligand atom. It behaves as one ligand atom. So the total steric number should be 6. So the overall structure would be octahedral, but you have 2 different kinds of ligand atoms, 1 double bond oxygen and 5 single bond OH. So it would be a distorted octahedral. Going down, boron hydride is an anion with 1 minus charge. So boron starts with 3 electrons in the valence shell. There's 1 negative charge, so that make it 4, and it uses 4 to form 4 covalent bonds with hydrogen. So steric number equals 4. So this would be a perfect tetrahedral. The last one, xenon, has 8 valence shell electrons. Each oxygen requires 2 electrons to form covalent bonds, and each fluorine requires 1. So it will require a total of 8 electrons to form bonds with the ligand atoms. So again, there's no lone pair on the xenon atom. The steric number will be 6. Now, there are 2 different kinds of ligand atoms. Oxygens are double bonded, so those 2 double bonded oxygens will be in transposition to minimize repulsion. All right, going down here, point group assignment, HCl. There's not much to talk about. This is one of the special case, C infinity V. The second one, ethane in staggered conformation. This should be D3D. On the right hand side, I show 2 different popular conformations of ethane. There's eclipsed, where two sets of hydrogen atoms are exactly on top of each other. Okay? And there's a staggered conformation where one CH3 is rotated exactly 60 degrees from the eclipsed conformation. On the bottom, it shows the end view, looking at the carbon atom at the direction of the carbon-carbon bond. Okay, so in this view, you can see the C3 very easily. You can also see the C2s. Those C2s are perpendicular to the C3, and it goes through the center of the carbon-carbon bond. All right, so this would lead the assignment to D3D. You can also see the mirror planes that contains the C3 very easily in the end view. Okay, so it basically goes through the top hydrogen, the middle 2 carbon atoms, and the bottom hydrogen, and there are 3 such mirror planes. Going down, hydronium ion, this is basically another form of ammonium, so it should be C3V. The one down there is cis dichloroethylene. This is C2V. The C2 is in the plane of the paper, and it's perpendicular to the carbon-carbon double bond and goes through the center of the carbon-carbon double bond. The 2 mirror planes, one is the plane of the paper itself, another is perpendicular to the plane of the paper and goes through the center of the carbon-carbon bond and contains the C2. Going down there, dichloropherosin, this is C2H. The C2 goes through the iron atom and is parallel to the 2 5-member rings. Cyclohexane chair conformation, this could be challenging. So I showed a number of different views of the chair conformation cyclohexane. On the left is a top-down view of the 6-member ring where you see the C3. Okay, so the important thing here to note is that the chair conformation produce 2 sets of carbon atoms. There are 3 carbon atoms pointing up, having a hydrogen atom pointing up, and the other three, okay, have hydrogen atoms pointing down. Now the C3 will rotate each set of hydrogen atoms onto another member of its own set. There's also a C2, actually three C2s, and the structure shows one of them. The C2 is perpendicular to the C3, and it goes through two carbon bonds that are parallel to each other. So what I showed in the next three views is I gradually tilted the molecule, and this shows where the C2s are located. In the rightmost view, what you see are the top and bottom CH2 and the middle two carbons overlapping with two other carbon atoms in its back. Okay? And the C2 goes through these two carbon-carbon bonds. Okay? And you can see in this view that it can rotate the top two carbon atoms to the bottom, and it's a perfect C2. And there are three sets of them because there are three pairs of such carbon-carbon bonds. Going back to the first view, you can also appreciate the mirror planes that contain the C3, each going through two diagonal carbon-carbon atoms and perpendicular to the view. So this will lead the overall assignment to D3D. Okay, so the rest of the two problems are pretty straightforward, so I'm not gonna waste your time on it. All right, this will conclude our discussion today. If you have any questions, feel free to shoot me an email. Even though I'm out of town, I still have constant email access. I'll try my best to answer those email questions as soon as possible. All right, good luck on Wednesday.